Hi, in this video we're going to be looking at electric potential difference and electric potential energy. And one of the things we learned, and hopefully you saw this in the Nearpod, is that electric potential energy has some similarities with that of gravitational potential energy. And so, quick reminder, electric field is defined as the force per unit of charge. And so when you have an electric field going between something, so if we have an electric field, if we have a positive charges up here and negative charges down here, and I'll change colors with that, and then my negative charges down here, there's an electric field there that's going to go from the positive to the negative, and it shows the direction that positive charges would move as it goes through. So a positive charge, and I'll put this in green, would naturally want to go from the positive one down towards the negative. That's its natural progression. Kind of like if you took a rock and you dropped it. Whereas if we tried to take the object, and I'll put this in purple, if we took that positive one and we tried to push it back up, we would have to do work on it in order to do it. Very, very similar to if we tried to lift something up and raise it up to a higher height. Okay? So let's go back and take a look at that gravitational analogy. Okay, we have two diagrams, diagram A, diagram B, and here we have the rock that's going to fall on down. And so, is there work done on the mass? Not by us. And so, when it talks about this NC, they're talking about a non-conservative force. They're basically talking about, are we going to do work on it? So, are we doing work on it? The answer is no, it's not. But at highest potential energy, because of how we define potential energy, PE is equal to mgh, that should be an M, then we know the highest potential energy is going to be at point A. Now, if we look at B, now we're going to force this rock up. We have to exert a force on it. So is there work done on it by us? Yes, there is. But our highest potential energy, now it's that highest point, that's going to be at B. So we're going to apply that now to the same thing with the electric potential. This represents our electric field. So again, if I go back and remind you of this, when the electric field lines, these electric field lines show the direction that positive charges will move. So you can simplify and say, oh, well, there's a positive on this side, negative on this side. So if we go down and look at our pictures now, we can think, and I'm going to draw this once and then not again, we can think, oh, well, there's positive charges over here, and then negative charges over here. And so our electric field lines will connect the two. So as my charge sits right here, and I'll circle this in green, it's going to naturally want to flow from the positive to the negative. So are we doing work on it? No, not in this case. Because the electric field will, we don't have to. If it goes with the electric field, we don't have to do any work on it. But potential energy is still going to be highest at point A, and electric potential is going to be highest at point A as well. Now, real quick, electric potential is defined as the energy per charge. And so if you have a high potential energy, you're going to have a high potential. If you have a low potential energy, then you have low potential. Now, if we look at this next one over here, now we have this point A, and now we're going to move it over to point B. Now we have to go against the direction of the electric field. So now, do we have to do work on it? Yes, in this case we do, because we have to fight it. It doesn't naturally want to go from A to B. It would naturally want to go from B to A. But our potential energy is greatest at B, and potential energy, the electric potential is also greatest at B. If we go down, and I'll just do this one, then work our way around. Here we have a positive. Here's my positive plate. Positive is going to be on the bottom because the charge is going to want to naturally go from the bottom to the top in this case. And so, will we have to do work on it in order to push this thing back down here? The answer is yes. Okay, because we have to go against that electric field. So potential energy is going to be greatest at B, along with the electric potential. And then we look at the reverse. Here's A to B. Now, do we have to do work on it to make it go? No, it's naturally going to want to flow there. So no is work we have to do. And potential energy is highest at A. Okay? So you can think about it. It's going to naturally want to go from high potential energy to low potential energy. So in the direction of the electric field, that's the way it's going to want to flow. So if we go with the electric field, we don't have to do work on it. The electric field will. And if we do have to do work on it, if we go against that electric field, then we have to do work to fight across that. Now, this is a big deal when it comes to electric circuits. This is a big idea. When work is done on a positive test charge, to move from one location to another, potential energy will increase. If we do work on it, the work we put in goes into an increase in that potential energy. And electric potential will increase as well. And so the energy per charge will increase as well. So if we have to do work on it, we put energy into the system, then the potential energy and the electric potential will go up. So if it moves naturally from one location to the other, the potential energy in that case then will decrease along with the potential difference, or sorry, electric potential. Okay, so if we're talking about circuits, okay, we looked at this circuit. We have a 12-volt battery here, okay, and so charges are going to naturally want to flow from the positive to the negative. Because remember, we're talking about conventional current. Remember the whole Ben Franklin conspiracy. Ben Franklin said that positive charges moved, and we still believe that today. Well, we don't believe it. We know that's not true, but we still accept it and use it as our thing. But it says the diagram at the right shows a light bulb connected to a 12-volt car battery. The positive and negative terminals are shown. So you can think of the positive terminal as being like a positive plate. The negative terminal is like a negative plate. So as charge moves through the battery from D to A, it's going to have to gain potential energy because we're going to have to do work on it. It wants to stay at the negative. We're forcing it to go to the positive, so it's going to gain potential energy and gain electric potential. The highest point of the battery is the positive terminal. Okay? Positive terminal is going to be that highest point. Now, if it goes from A to D outside of the battery, it now is going to lose potential energy and lose potential. And the highest point there is, again, still the positive terminal. The highest point is still the positive terminal. It's just it naturally flows outside of the battery from A to D, and then we have to force it to go from there, from D to D. Or sorry. So if we look at the voltages here, how much energy, how much potential it has. Okay, this may seem a little weird, but it's asking for how much energy there is. And so at VA, that's going to be, okay, actually VB and VA are going to be the same. They're going to be the exact same. So they're going to be equal to each other. Same thing with VC and VD. They're going to be the same. And the reason for that is it takes very, very little energy to move from A to B. Okay, there's no resistance there, so they're basically going to be the same. But the electric potential is going to be greater, VA to VB, because it's higher, closer to the positive plate than it is to the negative plate. Now, this role of the battery in electric circuit is described in three different ways. It is the energy side. With a battery, batteries supply the energy. They don't supply the charges. They supply the energy to get them to move. Okay? And again, that energy that's in the battery will do the work upon the charge to create that electric field. And then third, by moving the charge against the field by negative positive, that establishes an electric potential difference across those two ends of the external circuit. So electric potential difference is also called voltage. And voltage is the change in potential between 2 points. And it is equal to the work done divided by the charge. So we can write this equation as V is equal to W over Q. So if we look, it takes blank joules of work to move 1 coulomb charge from the negative to the positive terminal of a 1.5 volt battery. So in this case, it's going to take 1.5 joules of work. And the way I got that, I knew that my voltage, hang on, I'll put this in red. My voltage was 1.5 volts. My Q was equal to 1 coulomb. And so by cross multiplying, I can solve for the work done. It's going to be 1.5. Now, it'll take, if I want 2 coulombs of charge to move to the 12-volt battery, now here, this is going to take me 24 joules of work. And the way I got that, again, I'll put this off to the side, I know that my voltage is 12 volts. I know my charge is equal to 2 coulombs. So I can find the work done. Work is equal to voltage times charge. Cross multiply gives you 24. It says it takes 18 joules of work to move blank charge from the negative to the positive terminal of the 12-volt battery. So in this case, I know the amount of work done. Hang on, I'll put this in orange. The amount of work done is equal to 18 joules. And it gives me the voltage is equal to 12 volts. And we're looking for the charge in this case. So if I'm trying to find charge, hang on, we can just solve this for Q. Actually, I'll just put it right here. So 12 is equal to 18 over Q, volts, coulombs. So I can find my charge by doing 18 divided by 12 and coming up with 1.5 coulombs. The next one, it says it takes 12 joules of work to move 2 coulombs of charge from the negative to the positive terminal of a blank volt battery. So now we know, and I'll put this back in blue here, so we know our W is 12. And we know our charge is 2. And we're looking for the voltage. So V is equal to W over Q. So in this case, it's going to be 6. Now, it's going to be 6 volts. Remember, you could also put that in, if you use units-wise, this was 12 volts, or sorry, not 12 volts, that should be 12 coulomb, or 12 joules, I apologize for that. So I've got 12 joules over 2 coulombs. I can put that as joules per coulomb, and that'd be perfectly fine. That's also known as a volt, however. And lastly, it takes blank joules of work to move blank coulombs of charge to the negative positive terminal of a 12-volt battery. And we can make this whatever we want. If we made this 1 coulomb of charge, then we would know that it would take 12 joules of work. If it took 24 joules of work, or 24 joules of work to move 2 coulombs of charge, so on and so forth. And lastly, we look at this in terms of the battery supply here, and this is kind of an electric potential diagram. So at point A, it's going to have the highest, but it's also going to be at point B. And the reason for that is because in moving from A to B, it takes very, very little energy to go from there because it's a conductor. Now the light bulb that's in between B and C, that one right there, that is a resistor, and so it's going to take some energy to move there. So when we move from B to C, it's going to take some potential to get it down there. So that'll be point C. But going from C to D now is going to take roughly the exact same. I'll put this in orange. So C to D, again, because we're moving through a resistor, C to D is going to be roughly the same as it was before. And then we have to go from D to E, and then D to E, it comes all the way down. I'll put this in red. So D to E comes down to there. And then E to F is the exact same because, again, it's going right through. And so that's going to be that 0 volts. So I like drawing it out like this. You could also put it in here and say, oh, well, this is A and B. Again, I'll put this in kind of a pencil. So this is A and B at the 12. A equals B. Let me rechange that. A equals B. And then down here you can do, oh, well, this is C equals D. And down here, this is E equals F. And so you could also do it that way as well. Okay. But I kind of like drawing it out so it's a little bit easier to see. Okay, so hopefully this answers a few questions on voltage and potential energy. And if you have any other issues with it or questions, try to take a look at some of the should-dos. So everybody have a great day. Have a great night. We'll see you later. Bye.